Before inviting our speaker to the stage, I would like to invite Professor therein from Harvard to introduce the topic. Thank you very much.
I wanted to talk a little bit about Mike. He studied physics at UCL in London, and completed his PhD in 1980. He won a science and just an EPSRC fellowship in 1982. A Royal Society University Research Fellowship in 1983, and then he moved to Swansea and became professor and head of department a bit later here in Swansea. He held an Engineering and Physical Science Research Council senior fellowship from 2007 to 2012. That was the last, I think. You were the last one who got that scholarship.
They abolished it after me. They abolished them after me.
And the was the co-representative of the 2011 American Physical Society Dawson Award for Excellence in Plasma Physics Research. And also in 2020, he got the Physics Conference Medal and Prize. He is a fellow of the Institute of Physics and a member of Academia Europea. And he was elected as an inaugural fellow of the Learned Society of Wales in 2011. And is currently its vice president for STEM, double M. So Mike started with the idea of making antimatter in 1986. 11 years after he finished his school. Yeah. He first worked on LEAR. Thus, in CERN, we have antiprotons, and the antiprotons were used for other purposes. There was an antiproton and a proton collisions in CERN, and they tried to look at things. But in LEAR, you could also get antiprotons in a beam. Then he worked already in LEAR and tried to catch antiprotons in a magnet. However, at some stage, CERN closed it and used it for other purposes. However, just in the last moment before closing LEAR, in 1995, the first antihydrogen was observed. By a process, okay, I won't go into that. Maybe you show, I don't know.
No.
I can remember it. I think it was in 1996. I was just a postdoc at the Royal Holloway working with positrons, and I knew Mike from. He probably didn't know me, but I knew Mike from a meeting we had about getting a LINAC. UK-wide LINAC for positron prediction hasn't happened. And then Mike had an interview with TV channel. I don't know, was it BBC or?
I can't remember. He was an independent program maker.
The interview was shortened on the television. And I saw it, and I think it mostly was to say what or whatever.
Yes, that was my reaction to her question was what? And that's all they played of my interview.
That was okay, however, this research from that making antihydrogen made CERN realize that this would be important and started making the antiproton decelerator in CERN. And then Mike and other people made a collaboration, a TINA collaboration, and they needed a postdoc for that. Thus, I became a postdoc for the TINA collaboration with Mike in University College London, and we made the first positron accumulator, because when making antihydrogen, you need an antiproton and positrons. Thus, we did that. I'm not sure that without Mike, the Athena collaboration would have been formed and was successful, because he got a grant of 359,000 pounds for the accumulator and going on. Furthermore, because of that, the antenna was produced in 2002. We produced the first cold antihydrogen method. Thus, the first antihydrogen methods were going at very high speeds, made and detected. But in this case, we made them cold, and cold means a couple of Kelvin. Had it not been the case, then I don't think, because CERN had ideas in 2005 to clone the antiproton accelerator, and I don't think if he hadn't made the antihydrogen, that would have happened. Because I think, due to Mike getting the positron accumulator and forming the Athena collaborations, we still have the AD, and from there grown to the alpha collaboration. Presently in Swansea, we have about 15 people working in alpha collaboration, and Mike will talk about that, I think. And
if I get the chance.
I have 3 minutes. Am I over 3 minutes?
Yeah, you can start with that.
Okay, very, very good. But also, Mike is very well known in the world in positron and antimatter. But also, I want to mention is Mike also was instrumental in getting a lot of people in Swansea. Because without Mike, we wouldn't have probably that many people. I'm an example of it. Sorry, Mike. But other people as well. So, for instance, Stefan, Niels, Arlet, and Chris Baker are all here because of Alpha, because of the things. But also more people in the department were here with the mic.
Thank you very much. Thank you, Dirk.
Yes, you're welcome.
Thank you very much for that generous introduction, Dirk. Yeah. So I hope that I'll be able to explain to you in this talk what these two images mean, these sort of iconic images. This is one of the first images of antihydrogen produced, as Dirk mentioned, in the Athena experiment. And that's an antihydrogen atom annihilating. And this is a depiction of an anti-atom trap with antihydrogen in. And we are now able to do this routinely. So I'm going to talk about physics of antimatter and some applications. And one of the applications is going to be this. And you might wonder what a laser hybrid accelerator for radiobiological applications is doing on the back end of an antimatter talk. But I hope it'll become evident towards the end. Oh. It's frozen. Or something is gone. Oh. Ah, okay. Does it work with this type? Oh yeah, perfect. Okay, thank you. So yeah, these are really high up, so I'm going to have to move these. So this is one of my great heroes, of course, and I hope yours too. This is Paul Dirac. He won the Nobel Prize in 1933 at the age of just 31, essentially for this equation. This is the longhand version, as he wrote it down originally, of what we now call the Dirac equation. It's got electric and magnetic fields in here and a few other things. And if you put them to 0 and solve for W, which is with the energy in those days, it's E nowadays. But if you solve for that for a free particle, you get the familiar relativistic. So Dirac was He was the first person to successfully unite quantum mechanics and special relativity. The Schrödinger equation is not Lorentz invariant. So he united those, and this is the solution of this equation for a free electron. And this is a familiar m0 squared c to the fourth plus p squared c squared to the half. But you'll note that Dirac obtained not only these solutions, two others as well for spin, but he could not neglect the negative energy solutions here. And eventually, the picture that emerged from his work was the following, that he surmised that these negative energies were completely full and uniformly distributed and were not observable unless you supplied at least that amount of energy, 2m0 c squared, in which case you could get an absence of a negative energy electron, which was interpreted as a positively charged particle with the same rest mass as the electron. And this is the positive electron, or what we now call the positron. So it took Dirac quite a while to sort, 3 years or so, to sort out this interpretation. And during that time, there'd been an awful lot of skepticism about his equation because of these negative energy solutions. And so he was occupied in 1931 writing a paper called Quantized Singularities in the Electromagnetic Field. In that paper, he showed that if the magnetic monopole exists, then charge is quantized in units of E. But at the start of the paper, the first few paragraphs, he says, I've got to sort out this issue with the negative energy states. And he writes 3 or 4 paragraphs at the beginning of this paper on this topic, something we would never ever do nowadays, mix papers, subjects up like this. But this is what he wrote about the positron. We should not expect to find any of them in nature on account of their rapid rate of recombination. That's what we now call annihilation with electrons. But if they could produce experimentally in vacuum, they should be quite stable and amenable to observation. The final 18 words of that encapsulate my entire career. Okay, so that's what Dirac wrote at the beginning of this paper in 1930. When you remember at the time, there was only 3 particles known: the proton, the electron, and the photon. The neutron was to be discovered in 1932. So Dirac added another particle, the positron. But 2 paragraphs later in this paper, he says the following. Because his theory was not about protons, and initially he thought the positive charge in his paper was the proton, and there was some discrepancy with the mass that would get sorted out. It wasn't true. This is what he wrote in this paper. The antiproton, presumably the protons will have their own negative energy states, all of which are normally occupied, an unoccupied one appearing as an antiproton. I think that is absolutely staggering that a person can have such insight and faith in his theory. So it's a remarkable paper indeed. Didn't have to wait long for experimental confirmation. This is one of the early photographs of a positron from Anderson, a cosmic ray photograph of the cloud chamber positron, cloud chamber photograph. And the key to this working, there's a magnetic field here. I don't know which way it's going, but you can see, and there's a thin lead plate strapped across the center of the cloud chamber. And you can see the radius of curvature is larger here than it is above the lead. So the particle is coming in this direction and losing energy. And that enabled Anderson to pin it down as a positively charged particle. And from the track density and curvature, he could work out that it was something of the order of the electron mass. That was followed smartly by pictures of electron pair, positron pair production. So there's a big event up here producing a lot of electron positron pairs. So this is a work from Blackett and Occhialini in 1933. And in fact, positrons had been observed before this, but people didn't know what they were, and they failed to know the direction of travel. So they thought they were electrons coming up their apparatus, and not positively charged particles going down. But this is pair production. So every time we make a positron from the energy, you have to make an electron-positron pair. That's got something to do with symmetry, right? So let's look at antiprotons. How much energy is needed? Well, that's what you need. It's 930, so it's about a giga electron volt. And this is much, much, much greater than nuclear energies. Nuclear energies are typically, at least for the particles that are emitted, are typically millions of electron volt, not hundreds of millions. So as Dirk mentioned, to get access to antiprotons, we need accelerators. And you use just basically a brute force approach. You smash a high energy proton into another proton, and out comes another proton and an antiproton if you're lucky. So you can capture about 1 in a million of these and make them and do something with them. But that's the process that is used to make antiprotons. And it took a while for them because they needed accelerators. Essentially, they had to wait until after World War II when physics got back online and accelerators start to be made. And so antiprotons were discovered in 1955. So this is several billion electron volts. So that's a gigavolt nowadays, and a beamline here. And so these are timing graphs. That's a meson, a muon, and this bunch of particles here, this is time of flight. You can see how things move on. This is nanoseconds, but they called them millimicroseconds in those days. So that's the antiprotons there. So 1955, the antiproton was discovered. So it was pretty obvious from then on that you could make antihydrogen atoms if you wanted to, because you had both ingredients. But at the time, no one had any way of knowing how to slow them down, because if you want to get them to make an atom, they've got to be going at comparable speeds to one another. Otherwise, it's hopeless to get them to go together. So, positron annihilation. So, positron annihilation turns out to be a very, very useful thing. And this is really where the application of positrons come from. So, when positrons are emitted, positrons are in this room, and now there are cosmic rays coming down, there are high energy positrons coming out as a result of the muons decaying. It's easy to get positrons from radioactives, relatively easy to get positrons from radioactive sources. And all of those positrons are energetic, typically hundreds of kilo-electron volts or millions of electron volts. And we would ideally like to have them at room temperature, which is 25 milli-electron volts, or 40 milli-electron volts if 3 over 2 kT. But it turns out that the probability of when a positron scatters off an atom or a molecule, the probability of it scattering off the atom or molecule and losing kinetic energy is about 6 orders of magnitude greater than it scattering off the atom and annihilating. So you get an awful lot of scattering events, but no annihilations. So the net result, magically, is that the positrons reach thermal equilibrium or thereabouts, and most of them do. A positron stopping in a metal will reach thermal equilibrium and annihilate in thermal equilibrium. So all of that excess kinetic energy, is dissipated in whatever medium the positron is stopping in. It can be interstellar space, it can be a human body, whatever it's stopping in, all of that kinetic energy is dissipated. So when the positron annihilates and you get the 2m naught c squared back again, there is very little excess energy. If there was, you wouldn't get 2 511 keV gamma rays. 511 keV is the rest mass of the electron and positron. So in order to conserve energy and momentum, the most probable event for annihilation is 2 gamma rays, and they come off back to back. So this is an extremely characteristic event, more or less back to back. Of course, there is a little bit of kinetic energy around, so it's not quite back to back, and they're not quite 511 keV, but they almost are. And that is something that turns out to be really, really useful. So this is some examples of where we can get our positrons from. We like sodium-22, so sodium-23 is the stable isotope. It's lost a neutron, it feels a little bit positive, and it decays by emitting positrons, and it's got a nice long half-life of 2.5 years. So that's good for our experiments because we put the source in the apparatus maybe once, or if we're unlucky, we have to take it out again and put it back in again, but we can leave it in for a long time. But that doesn't, and there are various other isotopes here, but that's not suitable for all things. For some applications, you might actually want a low lifetime, the order of minutes or seconds, depending on what your application. And so you can see here a number of other sources, possible sources of familiar elements, all of which can be made radioactive and can be readily incorporated in chemicals. Well, why would you do that? Because you want to exploit the imaging capability of the annihilation event that I just showed. So if you can make a drug or something like glucose, even radioactive, and inject it into a person, and you put them inside a piece of apparatus like this, you can take photographs of them. So this is a ring of gamma ray detectors sitting around there. A patient will be put inside there. The technique is called positron emission tomography, and you can take scans of, well, not just the brain, but the brain scans are hugely important. And since I've been working with positrons on the outside for a long period, I decided many years ago to volunteer to have positrons injected into me to see how that went, and that went fine. So this is my brain, slices of my brain in 1998. I think it's false color, but this is slices of so essentially chopping through my brain and lying them flat like that. And this is a study of the uptake of a drug. Oh, I didn't put it on here. It's the uptake of a drug called benzodiazepine, which is used in the treatment of epilepsy. And so I volunteered for this study when I was working in London. And so after the study, I rushed back on the tube to my lab and got the Geiger counter out and started looking to see where the radioactivity was. It was all in my bladder. So it was already working its way through the body. And this is another nice application. So this is a photograph of a real Rolls-Royce jet engine in a lab. They've seeded the oil in the jet engine, the lubricant, with a radioactive source, and they're taking pictures, and they can see where hotspots are, where the lubricant is maybe not being circulated well enough inside the engine. So the engine is actually running inside the lab. So this is courtesy of the University of Birmingham. About 20 years ago, I gave a talk in Cardiff, and I showed this picture. So what did the audience say? I took that photograph. I was on the team at Birmingham that did that. So that was great. He was very pleased to see his picture in my talk. So I want to go back to the physics now and ask a sort of big question. And the question is there any antimatter out there? By out there, I don't mean outside today. There's antimatter all around. Is there any antimatter out there in the universe? In other words, does the universe have an equal amount of matter and antimatter in it? Which you would think it would do, because of E equals mc squared. And if the universe began in a big bang with just energy, and every time we do that experiment, we have to create a pair of particles, a positive and a negative, a positron and an electron. So you would think that matter and antimatter would be balanced. So there should be some antimatter out there. Well, there is. You can get positrons in the sun. I'm not going to dwell on this, but this is a solar flare from July 2002. And that's the solar flare, but at the same time, it produced radioactive sources. And the average gamma ray power, you don't want to be anywhere near, this is 10 to the 11 watts. And it produced something of the order of a billionth of a gram of positrons, which is a lot of them if you can remember that it's 10 to the minus 30 kilograms in weight, the positron. Anyway, the energy of it is only enough to boil a kettle, so don't get excited about it. But yeah, there are positrons out there in the sun. there seems to be a huge black hole at the center of our galaxy, and this is a picture of that black hole, or whatever the object is, taken using 511 keV. So this is positron annihilation in the galactic center. It comes and goes, but it seems to be there most of the time. And there are about 10 to the 42 positrons annihilating there every second in the center of the galaxy. What these lobes are is a subject of ongoing discussion. No one really knows how the positrons get away from there and what they annihilate on, because they're very extended. But so there are positrons out there. And a few years ago, an experiment was launched, the alpha. It's confusingly called alpha. It's got nothing to do with the antihydrogen alpha. It's called the Alpha Magnetic Spectrometer, the AMS. This is a detector. This is a picture of it at CERN undergoing tests in a particle beam before it was shipped out to NASA. So this is an instrument which is still sitting up in space and is collecting data, although there may be even a second one up there now. There it is. It's collecting very, very, very high energy primary cosmic rays. So it's collecting the cosmic rays before they have a chance to reach the Earth's atmosphere. Once the cosmic rays hit the Earth's atmosphere, you get these tremendous showers that we can see, you know, very familiar to us on Earth. And if you ever operate particle detectors, you can't get around the fact that you've got cosmic ray events. So coming down to the ground in great showers. So this detector is sitting above the Earth's atmosphere and is looking, and it was searching for antimatter, antinuclei. It's seen plenty of positrons, it's seen plenty of antiprotons, it's seen other antinuclei as well, but nothing higher than, I think it might have seen an antihelium-3, but very few. But if they're looking for antinuclei with charge greater than 2, and they have not seen one. So far, there's no evidence that there is any bulk antimatter. It's not a simple thing to work that out, but so far there is no evidence of there being bulk antimatter in the universe. If there was a bit of antimatter sitting out there and it hit a matter, a galaxy, say, an anti-galaxy in a galaxy, the signature for that would be quite easily visible on Earth. So the gamma ray flux and all kinds of other things, we would know exactly what that would look like. There are very stringent limits are currently being placed on the likelihood of there being anti-galaxies in the vicinity of the Earth. So no is the answer. There doesn't seem to be. So a little picture of the universe, the birth of the universe. We thankfully live out here in this quiet region where the universe is very cold. We just happen to luckily live next to a star, so we can keep warm. But as the universe was cooling down following the Big Bang, there were a couple of events of what this is disappearance of positrons and disappearance, I think, of antiquarks. And the reasons for these events, the total disappearance of them seemingly, because there's no antimatter out there, so the total disappearance of these is not fully understood. So by several orders of magnitude. So the imbalance, it's what we know should be out there is it's much smaller than the imbalance we see. So there should be, put another way, there should be far less matter left to make the universe that we are made of than there is, according to the known laws of physics. There is a little bit of asymmetry there, we know about that, but it's nowhere near enough. It's 6 or more orders of magnitude too small. So there are puzzles. So the thought that we had, the thought that I had in 1986, funnily enough, was can we make on Earth the atom that the universe didn't get the chance to make? In other words, the antihydrogen atom containing an antiproton. And that was the basic motivation for it. Can we actually put these two together? So we started out on that. Yeah, so the motivation for doing that, okay, I'm actually going to skip through this quite quickly because it's a bit technical and I haven't got a lot of time. But It's connected, of course, to the matter-antimatter asymmetry in the universe. And it's probably not a surprise to you that the hydrogen atom has been studied in very, very, very great detail, and some of its properties are known to very large fractional uncertainties. So there's a ground state transition. If you don't know what hyperfine is, it doesn't matter, but it's a microwave transition. And this is the jump between the first two states in hydrogen, the ground state and the first excited state, both of zero angular momentum. And that again is known to large numbers. And by the way, there's no theory to compare this with, because it's not possible yet to calculate these to the precision that they can be measured. Okay, because uncertainties in the nuclear structure get in the way in the end. So it's not just QED, there's more needed. And of course, if you're thinking about making antihydrogen, you might want to try and test its gravitational properties if you can, because as you probably all know, general relativity is a classical theory, and that doesn't sit well with the way we've been trying to approach the understanding of fundamental physics for a century or so. There must be, we think, some more general theory of general relativity than the one we currently have, or it must fit in some way in which we're not sure of at the moment. So I'm going to skip these, but basically, if you want, you can have a look back later, but the low energy antimatter experiments can enable tests of fundamental principles of quantum field theories and general relativity, such as invariance theorems. So the fundamental one is CPT, the combination of charge changeover, so positive to negative, parity, x to minus x, and time reversal. You can use those symmetries pairwise or on their own, or in this case, in a triple whammy of the three of them together. And CPT would dictate that the properties of matter and antimatter should be identical. So either equal or equal or opposite. So the charge is opposite, but the same sign, the same magnitude. So I'll skip through these. So how do we go about making these? So I don't know if any of you sitting in here had the luxury of being taught PH 112 by me a few years ago, but I made you solve the equations of motion for the Penning trap in one of the workshops. So the Penning trap is a workhorse of our experiments. It's basically just got a set of cylindrical electrodes. You apply voltages to them, and it's got a uniform magnetic field running along the axis. And what happens is that the particle undergoes simple harmonic motion, 3 independent harmonic motions. It bounces backwards and forwards along there. That's that one up and down like that. It goes round slowly in a circle due to a magnetron drift, and then it does its cyclotron motion. So there are 2 radial motions which are coupled, and that's what makes this problem interesting, even in first year electricity and magnetism. So a simple set of electrodes like that with a uniform magnetic field along, with voltages applied to them, you can capture and hold particles in those traps. Now, so given that, we need to go to CERN to get to the accelerators, and here is a picture of them. So it's not to scale, that's the Large Hadron Collider there, and that's the antiproton decelerator there. So to make antihydrogen, obviously, we need antiprotons, and we have to go to the accelerator complex at CERN. So we have the antiproton decelerator plus, I mean, this is, Dirk mentioned that the antiproton decelerator was on the line for a few years until we got some physics results. But even better now, they've given us an extra machine which sits inside the antiproton decelerator. It's called the extra low energy antiproton ring. and it decelerates them down even further for us, because we want them at the lowest possible kinetic energies we can coming out of these machines to capture as many of them as we can in these penning traps. And you can only pulse voltages up to certain heights. You can't go up arbitrarily high in electric field. So the antiproton decelerator, it takes antiprotons, which come from, there's 10 to the 13 protons hit a target. That's roughly the kinetic energy as well. That's in a momentum, but it's roughly the same as 20 odd GeV. They smash into a target, make antiprotons. They're captured in this little ring here. This is and CERN is a magnificent place. It doesn't just accelerate particles up to the highest possible energies it can. It's actually figured out how to decelerate them. And that's not straightforward, actually, because once you decelerate a particle, if it has a certain speed, but it also has a beam, say decelerate a beam, the beam has a certain speed in the direction in which it's traveling, but it also has a temperature, which is distinct from the speed, okay? Only when you're in true thermal equilibrium are they the same. When you're not, the temperature is different. So you will have a speed, a kinetic energy, but you will also have a spread of kinetic energies, which is effectively the temperature. Okay, so if you decelerate the particle, so you reduce its kinetic energy moving along a certain direction, then the effect of its temperature becomes much more important. So the beam has a larger divergence and becomes harder to handle. So you have to remove that temperature. So you have to decelerate and cool, decelerate and cool, decelerate and cool. And that's what CERN learned how to do. I won't go into the details, but you have to decelerate, cool, decelerate, cool, decelerate, cool. You must cool. Cooling is really important. And then we can capture them. They come crashing in. We pass them very simply through a foil. There's another penning trap with its solenoid and electrodes. And we set a little trap for the antiprotons. It should be a positive hump, but never mind. That's a trap. It's more intuitive. It's a trap. And what we do before the antiprotons arrive is we stick a bunch of electrons in there. Okay. Now, electrons are marvelous things in a 3 Tesla magnetic field because they whiz round. Their cyclotron motion is very, very fast. It's 100 gigahertz or something. And they radiate their kinetic energy away. So that's how these things work. That's how the folding pocket works with electrons going backwards and forwards. So they radiate energy, cyclotron radiation. So the electrons, we capture them in there and they cool just naturally. And they reach effectively, they sit immersed in a microwave background. They effectively reach the temperature of the trap. The antiprotons come along. The antiprotons don't care that they're electrons. They're not antiparticles. So the antiprotons, they pass backwards and forwards through the electrons, and they lose kinetic energy to the electrons. And after a few seconds, say tens of seconds, the antiprotons are sat in a volume about the size of the end of my thumb, overlapping with the electrons. We can easily kick the electrons out. They have different motions, different frequencies of motions to the antiprotons, so we can remove them and we can leave ourselves with a pure antiproton cloud. So the antiproton thermometer there, that's where they start off in the LHC, or where they go in the LHC, or protons at a tera electron volt. We're sitting down here at minus 200 and something degrees centigrade. So we cool them eventually into the Kelvin region, so the order of 10 Kelvin. We like to get them as cold as possible. Okay, as Dirk mentioned, we have to accumulate positrons. They come from radioactive sources, and I won't go into the details, but we make a beam. But when you have a facility like CERN, the antiprotons arrive in a burst. So you know when they're coming, and you can dynamically change the parameters of your trap to capture them. But positrons coming from a radioactive source, you don't know when they're coming along. And so you arrange a fancy set of penning traps here. There's nothing unusual about these. Again, there's a magnetic field and a set of electrodes. And we have a set of traps for the positrons. And when they come in, we put a little bit of gas in, and they can lose some kinetic energy again before they'll much rather do that than annihilate. And then they will just slip down into this region here that we can just carry on accumulating them. And we do that. Don't worry what the two curves are, just the number here. So if this looks like a capacitor charging curve, it is. It's exactly the same physics as a capacitor charging because it is a capacitor charging. It's just charging with positrons, so at a constant rate. So you can get hundreds of millions of them, and we accumulate for many tens or hundreds of seconds, depending on the experimental conditions, but they're relatively straightforward. So we have to control these plasma. I'm not going to go into details, but we have to cool them and do all kinds of other things. But I just want you to remember that up there. So when you have a ball of charged particles, it's a cylindrical thing, it's an oblate spheroidal thing. It has a radial electric field, okay? This electric field is proportional to the density of the charge and the magnitude of the charge, and inside the plasma, it increases linearly with the radius. So, again, those of you who did pH 112, made you solve that as an application of get that as an application of Gauss's law. Yeah? No. All right. You can use Gauss's law very straightforwardly to get this electric field. So this electric field for us is an absolute nuisance because we've got an electric field in the plasma and we've got a magnetic field going along there. And what you get then is a tangential drift speed. So this electric field makes the plasma rotate like this. And this field to first order is not dependent on the mass of the particle. So if you put an antiproton in there, it starts to rotate as well with the same speed. And that becomes a physical kinetic energy, which the antihydrogen will get once you made it. So we have to keep these plasmas low radius because keep the antiprotons right on axis to make our antihydrogen to keep this tangential speed down. Anyway, we use evaporative cooling and other techniques to try and get the plasmas ready for mixing. And again, just back to annihilation, there's the positron annihilation. So when you make antihydrogen, if you don't do anything else, as soon as you make it, now those penning traps, it's not electrically charged, it's a neutral object. So it's not confined by the penning traps, it hits the wall and you get positron annihilation and then antiproton annihilation with a charged particle. So you get pions given off in that. It doesn't matter what they are, but you can see them coming off here. Several charged pions, another very characteristic signal. So you can locate the point at which the annihilation occurred, if you're clever enough. So that's where those two events come from in Athena. There's a back-to-back annihilation of positrons picked up by a pair of scintillating detectors, and then silicon pads around here picking up the charged pions coming off. So that's the origin of that event that was on the very first slide. It was the very first detection of cold antihydrogen. So if you want to track, so once we learned how to make antihydrogen, it was obvious to many of us that what we wanted to do then was to stop it, because it basically annihilated about a microsecond after it was made. And you can't really do many experiments. You can't do some, but you can't do many in a microsecond, at least not with something as rare as antihydrogen. So we wanted to develop a neutral trap. So you can make the atom has a magnetic moment, because it's got a structure, it's got a circulating charge, it has a magnetic moment. So there's an energy associated with that magnetic moment, which is the dot product with the magnetic field. And a gradient in this energy will produce a force. So if you can produce, so this, even though it's a tiny magnetic moment, you can produce a force. There is a force which can be produced from a changing magnetic field. So you have a sets of coils. So there's your penning trap for the charged particles, and you superimpose some set of coils, which will effectively make a magnetic field minimum. And if the kinetic energy of the antihydrogen is low enough, and look, it's got to be per Tesla of field change. And if you don't know how strong a field a Tesla is, don't go anywhere near it with anything magnetic because it'll just be pulled straight out of your hand. So Tesla is a huge field change, and the well depth for hydrogen and antihydrogen is about 0.7 Kelvin per Tesla of field change. So, and we only have a few centimeters in here. That's the radius of the trap. So we've got to get a Tesla field change over a few centimeters in order to make a magnetic trap that sits inside the region in which it's being produced, which is the vacuum chamber that the penning traps are sitting in. Okay, so if you just look at the grams, this is the energy levels of hydrogen, antihydrogen in a magnetic field, and you'll see that some of the energy levels have a negative. This is the Zeeman effect, basically. Some of the states, their potential energy rises as the magnetic field rises, and some it drops. So these, the ones that have a field that have an internal energy which rises when the magnetic field rises. So they are the ones that when they're approaching the wall of the trap, as the field is going up, they start to slow down. They lose kinetic energy, and if they've got a low enough kinetic energy, they will be reflected before they hit the wall of the trap, the metallic wall of the trap. Okay, so it's these are the states that can be trapped. If by exciting to another level, we can make the positron drop down to a different state, this state, then they're lost from the trap. So immediately we have a signal. So we can capture these in our magnetic minimum, and we can kick them up into another level from which they might well decay back into a level that is not trapped. And then they will automatically rush out of the trap and annihilate. So once we get on resonance with our laser, or whatever it is, we suddenly get annihilations when we hit the resonance. Okay. So that's what the experiment looks like. So there's the penning traps. There is the traps around there. The orange and the red are the magnetic minimum trap. There are the coils being wound of the. It's an octopole. So there are the coils being wound on the vacuum chamber. This is superconducting wire. So we're operating at Tesla type fields to make this magnetic field gradient. And surrounding the whole lot is an annihilation detector, a lot of silicon pads, and this is the detector that's picking up the antiproton annihilations now. We don't bother with the positron annihilation. We learned early on that we thankfully didn't have to detect that as well, because almost all the annihilations we see are due to antihydrogen formation. It turns out to be very efficient. So this is what our events look like. When an antiproton or antihydrogen annihilates, the antiproton gives out this vertex. And this is what happens with a cosmic ray. So we need to efficiently distinguish between these. And so that's what a cosmic ray looks like. It outputs a false vertex anywhere in the trap. But the antiprotons, of course, would all come from this central bit. This is the wall of the trap, the ring here. So we've learned how to distinguish these to a very, very, very high level, better than 1% in difference. Okay, I'll skip that one. Just to notice that antihydrogen accumulation for fundamental symmetry tests. So I haven't got time to explain this diagram, but just to give you an idea of the achievements that we've been able to get going in the last few years. We're now able to make antihydrogen capture a fraction of it, that fraction which is born with a kinetic energy below the trap level. And I didn't tell you this, but the vacuum inside this apparatus, because the apparatus is entirely cooled down, it's around about 5 Kelvin, everything on the inside. It's an extreme high vacuum. So we can essentially hold on to antiatoms for days. So what we now do is we don't waste a single antiproton, we just make antihydrogen all day long when the beam is coming, and we can accumulate it in the trap, and then we start doing experiments. It's quite incredible. So the lifetime of the antihydrogen atoms in the trap is at least 3 days. That's infinitely long for an atom, right? It's just incredible. So, all right. So this is one experiment we've done. You can see a resonance here. This is a typical, this is the characterization of the 1s, 2s transition in antihydrogen. This is the fundamental transition in hydrogen, which we're going to try to compare to. We're doing this in a magnetic field, of course. We have to have magnetic fields around for the charged particle traps. So in order to compare to hydrogen at the moment, we have to do an ordinary quantum mechanical calculation to get the hydrogen equivalent frequency. But to date, they're the same, to about a part in 10 to the 12, which is a good start. And we've also observed this transition and used it. So the 1s to 2s transition, if you remember your atomic physics, this is forbidden by a single photon because the states are the same angular momentum. But the 1s to 2p, that is the single photon transition. Now, this is a very, very difficult energy. It's 10.2 eV. It's in what's called the vacuum ultraviolet. So it's not even ultraviolet, which is bad enough because we can't see that. It's actually in the vacuum ultraviolet. So it will not propagate through this room. You have to have a vacuum that has to propagate through the vacuum. But so it's rather hard to make this light, but we have done so. Our colleagues in Canada were the first to come up with a new way of making a laser to do this, and we've observed this transition. Now, the importance of this transition is because it's optically allowed, you can use it to cool. So we now not only hold on to the antihydrogen atoms, we cycle them through this 1s to 2p transition to laser cool them. So we've taken them down from the order of 200 millikelvins to 20 millikelvin, roughly, relatively recently. So we can make antihydrogen, we can trap it, we can interrogate it with lasers, we can excite a cooling transition, or we can cool them and we can hold on to them. And then we can do our experiments, changing the state, and then perhaps having flipping to a different untrapped state and observe the annihilation as the signal for the experiment. So that's laser cooling of antihydrogen atoms, and you can see the collaboration. By physics standards at CERN, this is a relatively small collaboration, of the order of 50 people, but by university standards, this is quite a large collaboration. But as Dirk pointed out, Swansea has made many contributions over the years and recently to the team and to this achievement, which is basically going to revolutionize this field. So, and you can see we've got some preliminary data here. Just want you to focus on these two here. That is the line excited, the spectroscopy line without cooling. And you can see when we cool, it's narrower, as it should be. It takes longer to cross the laser beam, so it's narrower. So there's a transit time effect. Okay, I'm going to skip this. This is my new pet project. So I realized that the conditions that we have, I'm not going to skip it. I'll just say a few words about it, but I'm not going to go into any detail. So this is my latest thing. So I realized that the conditions we have in the trap are almost exactly the conditions that were present in the universe when atoms first began to form. The density is right, the temperatures are okay. So we can now start to consider making objects like those, but with anti-atoms. So we can hold the anti-atoms for a long time. Can we see chemistry? So yeah, that's my latest thing is the bubble diagram, and these two things here are very, very interesting objects indeed. This one in particular. So in the next few years, the most accurate clocks on the Earth will be made from its matter counterpart, H2+, because some of the rotational and vibrational transitions in this molecule they're so long, so they have lifetimes of the order of weeks or months, the excited states. So you know what delta E delta T does then. The line width is really, really narrow for the transitions. Can be in certain states in these. So that's what this field is about. It's about comparing, or partly about, it's about comparing. It's trying to see if there's a dodgy clock, basically. Is the antimatter clock beating it the same way that the matter clock is? That's the fundamental goal of the work. So, 2 minutes at the end, how on earth can I claim that laser hybrid accelerator for radiobiological applications is an application of antimatter? Well, that's what the machine is going to look like. And Swansea has been asked to join in to work on these orange things here. They're called Gabor lenses. They really are named after Gabor, who came up with the idea in the late 1940s, and it's not yet been successfully demonstrated, to make a lens out of an electron plasma. So there is a plasma just like ours. It's a space charge lens. So an electron cloud, there's your Penning trap. We've developed all these exquisite techniques for manipulating antimatter. So electrons were relatively easy, but we have to make a fat, large cloud of them. But all of the techniques that we've been developed for our antimatter experiments can be put to work to make this new sort of lens for accelerators. And the idea is that, and that's its focal length, if you can work that out, and it comes from that radial electric field. It's that radial electric field that is the nuisance for our antimatter experiments, which actually provides the electric field that does the focusing of the particles. And the beauty of this lens is that it circumvents the use of conventional solenoids, which use a lot of copper, a lot of power, and a lot of water. And it will circumvent the use of superconducting solenoids, which use an awful lot of expensive kit, as well as cryogenics. So there's a huge move away in particle accelerator technologies, trying to move away from using these environmentally unfriendly techniques. And this cheap, with a modest magnetic field, an electron plasma that you can load from, something you can buy from a few £100, say, is one way of doing that. And as I say, it's come about because of the work we've done on antihydrogen, and we're about to start on this in the next few weeks. And it would be a tremendous story, I think, because the application for these is for cancer therapy. So this would be just such a tremendous story if the experimental advances that we've had to go through to create and capture antimatter leads to an application which has real benefit to humanity outside of physics. So finally, just want to acknowledge all my colleagues at Swansea. Dirk has intimated that quite a number of us and a lot over the years have contributed through the Alpha and Athena collaborations, and now joining this new consortium to hopefully make this new type of accelerator for biomedical applications. None of this would have been possible without the generous support from, in particular, from EPSRC. So we've had continuous support for this work since the late 1980s. And of course, none of it would have been possible without the support that we've had from CERN, which is so much more than just particle accelerators. It is truly an amazing place to work. And thank you all very much for your attention. That's
good. Thanks, Mike.
yes.
Any questions?
Good.
Does the scattering cross-section of the positron depend on its energy?
On kinetic energy? Oh, yes. Yes, yes. Very much so. There are a number of important processes. So from an atomic physics point of view, all the important stuff happens at kinetic energies lower than the typical orbital speed of the atom you're scattering from. So below, if you want that in a kinetic energy terms, it's below a few hundred eV, if you think in those ways. And below a few hundred eV, you get all kinds of interesting processes coming in, direct ionization and other things as well. But yes, it's strongly energy dependent. And then of course at high energies, it just tails away in a well-known fashion. But yeah, very energy dependent. Yeah, go on then.
How do you screen the other products from the P plus P reaction when you're making antiprotons?
Screen, I mean, get rid of them.
Yeah.
Well, you set up a special. It's basically a huge, great horn that captures the negative energy particles, the antiprotons, with a certain range of kinetic energies. So yeah, it's not difficult to do because they're not confined that well, and they certainly won't be confined going around the machine. You know, they have a range of kinetic energies. So
Anyone else?
yeah.
So obviously, wonderful achievements during your career. And I'm sure you wouldn't have imagined, collecting, storing for multiple days and then dropping antihydrogen back when you started. That must have been a very distant speculation.
Yeah, but we did. No, yeah,
What you're doing now
it was. We had to make to get even any kind of a hearing. We had to make arguments for why it was worth doing. So all of these things were discussed at a certain level. But of course,
to the people today who are just starting out their research career, what would you say their big dreams 30 years in the future should be?
Well, think 10, start with, not 30, because it'll take you 30. So just think 10 to start with. I don't know. It was sort of accidental in a way. It was serendipitous how it started, just a chance conversation. So I had no idea that there was a source of low energy antiprotons in the world. And just a chance conversation with somebody, he said, "Have you not heard of this facility at CERN?" I said, "No." I said, "Wow," because I was so wrapped up with low energy positrons and using them for all kinds of scattering phenomena and what have you. It hadn't occurred to it. And once I'd heard that, I mean, it started straight away. We were talking about it the next day, all day, the possibility that we'd actually put them together. Because although it was very challenging then, because some of the techniques for holding the antiprotons, slowing and holding the antiprotons, were yet to be developed, they soon came online. And then it became, within 2 years, it was obvious that sooner or later, someone was going to put them together in the way that it was finally done in 2002.
Anyone else?
You just don't close your mind to things like that when they come, because you never know when they're going to come. So if you're out there, go to conferences, talk to people, listen to what they've got to say, sometimes hidden away somewhere you never even think about, a talk you wouldn't normally go to. You think, just going to go to the pub or something, I don't want to listen to this. And then all of a sudden, Yes.
What are the typical energies of the antiprotons before you actually gather them?
Well, coming out of the antiproton decelerator, they're 5 MeV, So that's quite a lot. So we pass them through a foil to slow some of it. It's crude, but coming out of the new machine, they're 100 kiloelectron volts. So CERN have now been able to, and for CERN, that's like stopped, right? 100 kiloelectron volts, it's zero energy. And that is really almost getting to the point where you could think of pulsing something on to capture them. But in any case, even if you use a foil, it's much more efficient at 100 keV than it is at 5 MeV.
Yes, follow-up question is whether there are any prospects for thinking about antiproton fusion.
Well, I think if the negative muon didn't work, I don't think, well, I don't know. I think there've been some experiments, but they annihilate very rapidly because they quickly, if the antiprotons quickly find themselves in a state where their overlap with the nucleus is non-zero, and then they annihilate. So they basically annihilate as soon as they stop the antiprotons, which positrons don't do. They move around for a while. And then,
Any other question?
Similar to that, like for party pressure, can you do like anti-deuterium or helium or anything, or is hydrogen still as far as you can do?
well, every time you add another, in principle, yes, but every time you add another quark on, or another particle, so another set of quarks, you lose 3 orders of magnitude. It's just sort of, I don't know why it's 3 orders of magnitude, but it is. So your flux of anti-deuterons is 1,000 times less than your p bars. Your flux of tritons and anti-helium-3 is 1,000 times less again. So where we're getting 10 to the 6 to 10 to the 7 antiprotons, we'll be getting 10. So anti-deuterons are just about feasible, but at the moment, it would be just really a stunt. We need to have more physics justification for doing such difficult experiment, because it would commandeer a lot of resources at CERN to try and learn how to deal with instead of having 10 million particles going around, you have 10,000. And that's a different order of magnitude. You just work the current out. Say, just put the speed of light in for argument's sake, and you work the current out. It's very hard to detect that. You have to be able to detect these flashes going past and tweak their orbits in the accelerator, otherwise they'll just be, or decelerator, otherwise they'll just be lost. And that gets really hard when you've only got a few of them. So the deuterons are just about feasible with a lot of effort, but I think there's not sufficient physics motivation at the moment for doing it. But yeah, in principle, there's nothing. The same processes we use to make antihydrogen would work just as well if we could get them. So we could easily make anti-deuterons, anti-deuterium, anti-tritium, you name it. We could make anything if you gave us the anti-nucleus.
Okay, last question. Peter?
That's great talk. Really was intrigued by the last part. Talked about Lara and your Gabor lens.
Yeah.
1947.
49. Yeah. Yeah.
Just tell you a little bit more about why your technology is going to be really useful for that ion beam. Is it because the ion beams are getting heavier and therefore they need more condensing? Is that the process?
I think that well, I tried to describe the motivation in terms of making a simple, inexpensive lens which didn't use a lot of power. It also turns out it's quite versatile focusing system. So the idea of that of Lara is to be able to use ions up to fully stripped carbon. Yeah. So a variety of ions. So not just proton therapy, but ion therapy, which can be much more effective in certain tumors, I'm led to believe. I'm just getting my head around that sort of stuff now, but yeah.
It's great that you've got the technology now.
Yeah.
That original thing.
Well, I think that what the appealing thing is that, and again, I didn't really say this, but the charged particle plasmas, we could hold on to them for days as well. So we've got techniques to load these plasmas and diagnose them and manipulate them into the states we want. We've had to do that as a necessity to be able to trap antihydrogen. It turns out that most of these techniques will just, despite the fact the plasmas are fatter and longer, but they would just go straight over into this lens. So we'd be moving from plasmas of a couple of millimeters of radius and a centimeter of length to plasmas that size and that low. So that's the sort they would have had in the physics department in the 1950s. It's going back to the, yes.
Okay, I would like to thank
Yeah.
Jenny. Don't meet again. We have tea, coffee.
Okay. And please feel free to talk to Mike more while you are having your that becomes acting.